Hello everyone, welcome back. Gustavo here. Today we are going to review and learn about an algorithm called the Shunting Yard algorithm. And you know what, to give you a spoiler already, this algorithm is basically for us to try to solve that thing right there. Arithmetic expressions, very simple things like 1 plus 4 times 2 minus 5. You can have parentheses as well. So if you have an expression and if you need to go and parse that expression and actually evaluate respecting the precedence order of operators, right? As human beings, we have learned that we have to multiply that 4 times 2 before we perform the addition and before we perform the subtraction, right? So we know that as human beings, but how do we instruct the computer? How do we tell the correct order and the precedence level of each one of those operators? This is what we're going to see right now, right? In the school right now, we are in this kind of compiler mood, right? We have this new course on compilers, and the Shunting Yard algorithm is simple enough that I thought it was appropriate for a YouTube short video. I'm not going to worry too much about how long this explanation is going to take, right? I'm going to go against what YouTube tells me to do. I don't care how long this is going to take. Let's just take our time and savor this explanation, all right? Before I start talking about solving expressions, parsing this input of characters, and actually evaluating and getting a result out of this, let me just tell you that when I was really young, right, as I just left my bachelor's and my undergraduate degree, one of the first jobs that I got, it was as a graphics programmer, right? So we used to work with this almost like this CAD system that had this kind of 3D system that you could go and drag and drop environments. So we work a lot with architects, and then you could generate this layout of a room so the architects could go design the furniture, and then you could go and drag and drop and ultimately render the project. And speaking of this kind of 3D rendering and this furniture and talking with these architects, one of the things that I was responsible for implementing, right, as I just entered, almost like the first month of working at the job, one of the first things I had to do was I had to create a small tool that we would provide to the architects and these people that was configuring the furniture and configuring the position of things. This tool, we should allow the architects to go and input a formula to specify things about a certain furniture. So let me give you an example. Let's just say that you have a furniture and that furniture has 2 doors. The architect should go and configure how much, what was the angle that that door could open. Should it open like this or should it open like this? So for us to specify what was the pivot point of that rotation and what was the actual distance that it could rotate and the angle, all these things, they were inputted as a formula, right? So you had a little expression that the architect could say, based on the parent object, you could rotate this many degrees. So it was the parent object plus 90 minus 70 minus the distance. So you have this kind of formula building tool. And that was just, I think I was like, I don't know, 21, something like that. I just left college, and I think, as most of you, I took compilers, I took formal languages in college, and I didn't really understand too much the applications of those things, right? I was too young, that is how it goes. And just to give you an example of how these things, sometimes we think that we're never gonna use these things in the real world. And as I just entered the industry, I had to go and improve my chops on this whole parsing expressions and kind of formal languages, things that kind of go hand in hand with what we learn in a compiler class. Right, so one example of solution, right? One algorithm that we can use for this type of things, very basic, super simple actually, is called the Shunting Yard algorithm. The Shunting Yard algorithm was proposed, I'm not going to say created, but it was basically proposed, right? It was published back in 1961 by Dijkstra, the famous computer scientist Dijkstra. He published this algorithm in 1961, and the name Shunting Yard is basically because, as you will see very soon, the algorithm resembles a lot this kind of railroad shunting yard that you can kind of go one way or go the other way. That is why it has this name. You know what? Let's just cut to the chase and learn what this algorithm is all about. If you have an expression like that, we're going to start the algorithm by assuming that we're going to have all those operators, as you have plus, multiplication, minus, we're going to have in our source code, of course, a table of precedence, right? So we're going to have that each one of those operators, they are going to be mapped to a precedence level, I would say. So how high in the precedence, in the order of operations, those things are. We know that multiplication and division, they have higher precedence than subtraction and addition, right? So that is going to be, our table of precedence is going to be something very similar to what you're seeing there on the left. Because we are going to start by assuming that we have this configuration right here. So look at what we have. We have right here on the right what I'm calling our input, right? So already tokenized, so we're going to go and split all that input into tokens. So we're going to have a number, right? An integer number, an operator plus an integer number again, an operator times integer number, operator, integer number. So we're going to have this digits, operators, digit operators, everything tokenized, right? Almost like in this array form, element by element. This is the input, and then on the left, we're going to have two important areas. Right there is what I'm calling my output. So in the output, we're going to get, after we perform the algorithm, we're going to get the actual output there on the far left. And right here, do you see, we have something called the operator stack. So in a nutshell, this algorithm is almost like a shunting yard, right? A railroad shunting yard. We're going to decide from this input, are we going to go to the output or are we going to go to the operator stack? So basically, we're going to kind of define an algorithm to tell us if we are leaving right here, we're going to go to the output, or are we going to go to operator stack, and how do we populate that output in the correct order, numbers and operators, for whenever we go from left to right in that output, we're going to go and we're going to be able to evaluate this expression right here, right? That expression that you see right there. All good? So the first rule is, we are going to go from left to right, token by token. Let's look at this first one right here. The number one rule of this algorithm is, if we are reading from the input, this token right here, and if it is a literal number, if it is, let's say, a digit, an integer, that number goes straight to the output. We don't do anything. If it is a number, we just go straight to the output. So we're going to go, and that number is going to go to the output stack. All right? And now, if we find an operator, we're going to have to decide, is this operator going to go to the operator stack, yes or no? Well, since we don't have anything, this operator right here is going to go and pile on the operator stack. So it just goes and pile right here. Next token, digit. Easy, directly, right? Straight to the output. Now, here's the thing. This operator right here, we already have an operator in that operator stack. We're going to compare. Is the precedence level of this operator higher than the one that we have right here? If it is higher, we are going to pile on top of the operator stack, right? So since multiplication has a higher precedence level than addition, we're just going to go and pile on top. So this multiplication is going to pile on top of this thing right here. So now we have addition and multiplication on our operator stack. Next one, number, super easy, goes straight to the output. Here is the heart of the algorithm. Subtraction. Is subtraction greater or lower than what is on top of our operator stack? Minus, right? Subtraction has a lower precedence than whatever is on top of the stack. So what we're going to do is, since it is lower, we're going to go and we're going to start to flush whatever we had right here. So both multiplication and addition, we're going to go and move them to the output before we pile minus here. So these things are going to go first to the output. So multiplication goes to the output, plus goes to the output, right? We are going to pop and pop from this operator stack, move to the output, and only then the subtraction goes to the stack again. This is the base, right? This is the meteor part of the algorithm. These ideas of looking at the precedence level to decide what goes to the output and when they go to the output. Remember the shunting yard, railroad thing? We decide what goes to the output and what goes to the operator stack. And depending on the precedence level of each one of those things, we know if we go straight to the output or if we start piling before we go to the output right there. It's all about putting those things in the correct order so the numbers and the operators, they are respecting the actual operator precedence level that we have, right? That multiplication and division, they are going to be performed before addition and subtraction. All right, and then the last one right here, this is the last token, 5, no sweat, goes straight to the output. We are done with the input, but we still have some stuff here in the operator stack, so what we do is just move to the output, right, one by one. We just go and we empty the operator stack and we move to the output. That order right there, it might seem a little bit weird, right? 1, 4, 2 times, plus, 5, and minus, but that order right there, I don't know if you guys ever heard of something called reverse Polish notation. If you ever worked with calculators from HP, right, those old HP 12C, HP 48C, so they used to work with this reverse Polish notation. Instead of saying 2 times 3, you used to say 2 enter, 3 enter times. Right? So that is how we perform the multiplication. You have to enter the operands first and only then the operator at the end. This is kind of what we're doing right here. We're going to have the operands first, so the actual numbers first, and only then, final, right, postfix, we're going to have the operator that we need to perform. So given that this thing right here is in what we call reverse Polish notation, for us to actually evaluate and to solve this, we're going to go from left to right, performing those operators between those elements. You know what? Let's just see how this goes. We're going to have a new stack, which I'm calling the result stack, and we're going to go from left to right on this reverse Polish notation, this RPN format. From left to right, we're going to go one by one, populating the result stack. So let's just see. We're going to start with that 1 right there. So 1 is a number we push directly to the result stack. Now we go to 4. 4 is a number we push to the result stack. Move, we go to the number 2, we push to the result stack. So we haven't found any operators yet. It's all numbers, right? 1, 4, 2. If we find numbers, if we find these integers, we just go and we push them to the result stack. Now, in the moment that I find an operator, let's just say that times there, that times we're going to stop and we're going to actually perform the multiplication between those 2 previous numbers. Because think with me, multiplication is an operator that needs 2 operands, right? It is a number times another number. So what we're going to do is we're going to go and we are going to get those 2 previous values from multiplication. So multiplication, I look in the previous one and I perform 4 times 2, and I'm going to pop 4, pop 2, and I'm going to leave the result of that multiplication on the top of the stack again. So multiplication, 4 times 2, I look at this 2 previous value because multiplication is what we call a binary operator between 2 terms. 4 times 2, I pop the 4, I pop the 2, and I leave the result on top of the stack, which is 8. Does that make sense? So this 8 was the result of 4 times 2. And now I move to go to the next operator plus, same thing. Now I have an operator, so I'm going to perform the operation plus between the 2 previous values, 1 plus 8. I pop, I perform the addition, and I push the result on top of the stack, which is 9. Beautiful. Now I continue, I go to 5, it is a number I just push to the stack, and now I find a new operator, minus, and the final thing that I do, I just perform the subtraction between 9 minus 5 is going to give me the result 4. And 4 is my final answer. I'm going to have at the top of this result stack, after I evaluated everything from left to right, performing this reverse Polish notation evaluations, I'm going to have at the top of the stack the final result of my expression, because 1 plus 4 times 2 minus 5 is indeed 4. All good? Told you, right? A lot of talk, a lot of explanation, but the meteor part of the algorithm is quite simple. It's basically just a decision. We go from the input and then we decide. It's kind of Shunting Yard decision. Do we go directly to the output or do we pile operators in the operator stack? And then as we have the precedence level, we know what gets flushed to the output and the correct order that we need to perform this, the precedence level and the precedence order of operations. Does that make sense? The order that we have here in this reverse Polish notation, the goal of the algorithm, the price that we are after is we need to populate this output in the correct order, in this reverse Polish notation order, because as we go from left to right, we're going to start evaluating those things. We need to populate these things in the correct order to respect the order of operations, given that we have multiplication and division before addition, subtraction, and etc. If you have different operators with different precedence levels, the idea holds true. It doesn't matter how many operators you have, how many different levels and precedence levels that you have, you can basically just start adding. The algorithm, the logic holds true. All right? You know what? Let's just propose a quick exercise. I'm going to give you a new expression, and I want you to get some pen and paper and do that yourself. So right now, how about you try to solve this expression right here using the same algorithm that we just saw? We're still going to have the same precedence table where multiplication and division, they have a higher precedence than addition and subtraction. And you can go ahead and set up your algorithm in this format right here. You're going to have your input, your tokens, one by one, digit operator, digit operator, digit operator. And I already populated here, So you have digit, the operator plus has precedence 1, and then you have a digit 3, and then the operator multiplication has the precedence level 2. So you have all these different items. You have to just perform the same idea, going straight to the output or piling up on the operator stack, looking at the precedence level and deciding what gets moved where. Does that sound like a plan? I think so, I think it's a good idea for you to kind of go and perform that yourself. Look, I'm going to give you a couple of minutes. You can pause the video, try to solve that in a pen and paper. And as soon as I'm back, I'm just going to go and kind of run through my implementation of these things. So my logic and how do I come up with a solution for this thing. So go ahead, pause the video, and I will see you in about 10 minutes or so. All right, we are back. How did that go? Did you get the correct answer? Did you end up finding the actual order of elements and solving everything to give you the correct answer to that expression? If you got that, just give me a little hallelujah in the comments. I want to see how many of you got to this stage right here. Right, let's just stop talking and get to it. So how do we solve this expression right here? Right, first things first, number goes straight to the output. Now we have an operator, we don't have anything in the stack, so we just go and we push to the operator stack. Beautiful. Number again, straight to the output. Now we have this operator multiplication. Multiplication has precedence level 2, which is higher than 1, so all we have to do is pile on top of whatever we had already. So now we had plus and multiplication in the operator stack, just waiting here, We're going to wait here until we are ready to go and push them to the output. Now we have 2 goes straight to the output because it's a number. And now the same thing, Minus. Minus has precedence level 1, which is lower than what we had right here. So we're going to go and, since multiplication is 2 and addition is also 1, we're going to go and flush all of this to the output. So first we push multiplication, and now we push plus addition to the top of this output stack. And only then the subtraction gets pushed to the operator stack here below, following the same logic that we did before, Now 2 is a number, goes straight to the output. What about multiplication? So this one right here has higher precedence than whatever was on top of the operator stack, so we're just going to go and pile. So we're going to go and push to the top of this operator stack. 6 is a number straight to the output. What about plus now? Well, plus has precedence level 1, so we're going to have to go and look at the operator stack and pop everything that is higher or equals to that precedence level. So since plus has precedence level 1, both the multiplication and the subtraction gets pushed to the output. So this multiplication gets pushed to the output, and now subtraction gets pushed to the output, and only then the addition gets pushed to the operator stack. Now we still have this 8 here at the end. goes to the output directly, and then we just have this leftover addition on the operator stack. We just have to go and flush everything, empty, push to the output. Again, this thing that you see right here is exactly this expression that you see right here, which was written using what we call infix notation, because it is infix between the operands, right? The plus here, it is infix between 2 and 3. Now we have this reverse Polish notation where we have operand, 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 and then the operator that needs to be performed on these previous 2 values right here. This is what we call postfix notation, because the operator goes after the operands, right? It is postfix notation. Here was infix in the middle, here is postfix after the operands. Good stuff. So let's just quickly go and solve this, right? Evaluate this RPN expression right here. We're going to get a result stack, and we're going to go from left to right one by one, performing those operations as we find them. So as we start here on the left, 2 just gets pushed, is just a number. We go to 3, gets pushed again, is just a number. Next element is a 2, gets pushed, just a number. So we're just basically piling up, pushing operands. And now that we find an actual operator, multiplication, this multiplication gets pushed, and we're going to go and perform the actual multiplication with those 2 operands from the top of the stack. So we're going to go and pop 3, pop 2, multiply those 2 things, 3 times 2, and save the result back on the top of the stack. 3 times 2, 6, no surprises here. We continue, we find now a plus operator. This plus operator, being a binary operator, is going to be evaluated using the 2 terms here before. 2 plus 6 is going to give us 8. Boom. We continue, now we go to 2, is just a number, we push to the result. 6 is just a number, we push to the result. Multiplication is an operator that is going to be performed on 2 operands, so these 2 ones here on top of the stack. 2 times 6 is 12. We pop these 2 and we just leave the result on top of the stack, which is 12, the result of that multiplication. We continue, now we get a subtraction, and we perform the subtraction 8 minus 12. 8 minus 12 is minus 4, so we have minus 4 as this intermediate result here so far. Now we go, we find the number 8, we push, and we find the final addition performed between minus 4 plus 8, pop, pop, and save the result on top of the stack. Minus 4 plus 8 is 4, which is exactly what I'm expecting from this expression right here. Easy, right? I told you, nothing too crazy, just deciding what gets pushed to the output, what gets pushed in the operator stack. So we have those elements, right? The output, the operator stack, and everything has to do with the order that we're going to populate our output. So we start pushing and pushing things to the operator stack until they are ready to go and send to the output, so they get in the correct order in this reverse Polish notation that we need to actually evaluate our result. Good stuff? Right, so besides just using this very simple example, how about we implement this? Right? So we should be able to go and implement a very simple Python script. Let's just use Python, because Python is high level enough, so we don't have to worry too much about memory management. We don't have to worry too much about thinking about how many bits, how many bytes we're going to store for each one of those things. Let's just think about the very, very high level of this implementation right here, right? And Python is easy enough, so if you want to translate to whatever you want later, it's easier, right? So I think Python is the right decision right here. It might not be the fastest implementation, but yeah, I think it's good enough for what we need. All right, so here I am in my Unix terminal. Let's just create a directory called shunt, which is a weird name, but it will do. And let's just start shunt.py. I'm going to use VI, but you can use Visual Studio Code, Notepad++, whatever you want to use, right? It doesn't really matter. Any code editor would do. And let's just start, assuming that we're going to have an input. And in our case, it can be hard-coded. Let's just say 1 plus 4 times 2 minus 5, that first example that we had. And again, to keep things simple, let's just separate everything with spaces right here. So it's easy for us to tokenize. We're not going to create a super complex tokenizer. It's just going to basically split everything with spaces. And I'm going to say that our input is basically our input. All right? And I know that one of the first things that we need is that table of precedence, right? So precedence, let's just start by saying that. Let's use a simple dictionary that has multiplication is precedence level 3, division same thing, and then addition has precedence level 2, and subtraction same thing, right? So far this is our precedence table. We might add a couple of things later if we have other operators with different levels, but for now that's it. And I think we're ready to start our Shunting Yard algorithm, that logic that we just saw in the slides. So let me just perform Shunting Yard algorithm, which, given that we have already an input, right, we're going to have also two important lists or stacks, if you want. We're going to have the output, and we also have that operator stack. So let's just call this op stack. So the output is going to be that output that was always on the left of our slides, and the operator stack was that one on the bottom that we were piling all those operators until they were ready to go to the output, right? So output and operator stack, they are super important data structures that we have to create here in our algorithm. Right, so let's just think about this. We're going to have to go token by token of our input. So for all the tokens in the input, but I have to split, right? I'm going to have to split in spaces everything. So I actually have an array with elements one after the other. And let's just for the sake, let's just strip to remove any padding left and padding right on that input, right? So we're just going to go clean left and right and also split in spaces. Let me just make sure that everything is fine. So print token, let's see if that works. Right here. So Python 3 shunt.py. I expect to see. There you go. We had, for this string input right here, we broke everything into tokens, right? Just using split. 1 plus 4 times 2 minus 5. That is exactly what I expected to see. We are in good shape. So what do we do for all the tokens? Right, so first things first. If it is an operator, I'm going to have to do a couple of things. But else, if it is not an operator, if it is an actual number, I just add to the output. Do you agree? So output dot append, so I just go and I push to the stack of output that number, which in our case is the token. Right, so this is easy. This is just pushing the number. Push numbers directly to the output. How do I determine if it is an operator here? Right, so I do have these operators here in this dictionary of precedence, right? So let's just say that I can test by saying if my token is inside the precedence table, so meaning if it is an actual operator, here is where we're going to have to check the operator stack and perform that logic, right? I have to go and if the level of precedence is less than what I had before, then I had to go and flush and only consume those things. So I think I'm going to do this. I'm going to get the operator from the top of the operator stack. Right? So I'm going to look at that operator that is at the top of that operator stack at the bottom. So this is going to be up stack. How do I get what is at the top, meaning the last element? Well, I think Python allows us to do -1, right? I can have this negative index here. So here is where I get the operator at the top of the stack. And if the precedence of this new operator token from the input, if the precedence is greater than the precedence of whatever is on top, the operator that is on top of that up stack, If this is the case, I have to stop and not do anything, correct? But this is the thing. Let's just create a while. So I'm going to have to loop all the operators. So while I still have something in my up stack, while I have something in my up stack, if the precedence of the token is greater, then I'm going to break, because right here outside the while, I always will add up stack dot append, right? I'm going to push the token that I just got from the input, regardless of whatever happens. But if I didn't break, meaning if this thing right here is either less than or equals to the precedence of whatever is on top of the operator stack, inside this while I have to pop whatever was there, upstack.pop, and I have to add to the output. Actually, this thing right here, I'm going to move inside the while. Right, so I'm going to have inside my while, I get the operator and the top of the stack, and then I pop and I append that operator. Correct? I think this is the logic, right? Because I have to loop all the operators in the operator stack. I get what is on top. If by any chance the token from the input is greater than whatever was on the top, then I break. But if not, then I pop and I append to the output the operator, one by one inside the while. And this thing right here happens regardless. I always add, at the end, I add that final token. I push that token to the operator stack. Good stuff. And if it is a number, I continue pushing that token to the output directly. I think that's it. Right, so the one thing that I'm going to do is, at the end, we have to clean the up stack, right? So if there was still something there remaining in the up stack, I have to go and move everything to the output. Which means that while I have something in my up stack, let's append, let's just add to the output whatever came from the up stack. So upstack.pop. Cool, that should do it. Let's just say here, push the remaining operators from the up stack into the output at the end of all that logic, right? And right here, let me just print. This is going to be the output in Postfix, right? This kind of RPN format output. Actually, let's just join everything using commas. So comma dot join. I join all the elements of the output separated by comma. Cool. Let's see how this looks. So if I execute my script, precedence on line 21, there's always something, right? Right, so let's see how this goes. I had 1 plus 4 times 2 minus 5. The postfix notation in this reverse Polish notation form is 1 for 2 times. So I'm going to multiply 4 times 2, which is 8, and then I add 1 plus 8, which is 9, and then 9 minus 5, which should be 4. Correct? So I like it. It looks like this reverse Polish notation is correct. That is great news. You know what? Why don't we just go and we implement a very quick reverse Polish notation solution, right? The same way that we had that result stack before. Let's do that. So right here at the end, evaluate a list of items, of elements in postfix notation, right, or reverse Polish notation form. And for that we need a result stack, and for all the elements in my output, one by one, if it is a number, or if my element not in plus, minus, star, and slash, so if it is not an operator, well, let's just be smarter, right? If not in precedence, result.append, so I just directly go and I push my element. And in our case, let's just push the float cast of that element, because I want to actually, instead of having a string, I want an actual number, right? So let's just go convert to float. It doesn't matter. I think that's a good idea. But if it is not, right? So if it is not a number, so if it is an actual operator, it means that those operators, we need to get the two previous elements. So the left operand comes from result.pop, and the right operand comes from result.pop, right? So it is the left first and the right after. Wait. It's actually the other way around, right? We have to pop and pop, so the first thing that gets popped is the right hand side. So this thing has to be popped first. So I pop the right, I pop the left, and then I perform if the element is a plus, I push back left plus right. Correct? This is what gets the actual evaluation, right? This is what makes Python actually go and add those two numbers. And then we push to the top of the stack, and you know what? Everything else is going to be basically very similar to this. So if it is subtraction, it is left minus right. If it is multiplication, times right. And if it is division, it is left divided by the right. And I think that's it. At the end, I can print the result is whatever is on top of my result stack. Correct? So we just created a very simple stack solver here to solve that reverse Polish notation postfix list of elements, which means that, aha, there you go. So you see, result 4.0, I love it. I told you, everything is easy as long as you understand the algorithm and you kind of don't make any confusions, or if you don't break anything in this logic right here, right? As you are looping all the tokens, checking if it is operator, this logic right here of pushing and popping from the operator stack, not bad. Good stuff. And we could kind of call it a day, but there is a couple of things that I want to talk to you as well, because what about parentheses, right? Because I should be able to come here and have an expression of the type, I don't know, 3 plus 4 times open parenthesis 2 minus 1, close parenthesis times 6 plus 8. Something like that, right? I can specify that. Look, regardless of the operator precedence, you have to perform this thing right here first, right? You have to change the order to make whatever is inside parentheses first. And we should be able to do that as well. The shunting algorithm allows us to do that. We just have to think about what happens whenever we find an open parenthesis and what happens whenever we find the closing match parenthesis for this expression. So let's just discuss quickly that thing right there. All right, so here we are. 3 plus 4 times, and then we have now open parenthesis 2 minus 1 times 6 plus 8. So we have to think about parentheses, right? We still have the same precedence order, right? That table of precedence, that doesn't change. And our algorithm, we just have to decide now, right? Now that we have the same configuration, we have the input token by token, we're going to have to decide what goes to the output and what goes to the operator stack, and when those things actually get ordered to go to the output in the end, right? At the end, how do we organize everything in the output in that reverse Polish notation postfix form? Right, let's just perform the algorithm as we know, and then whenever we get to the open parentheses and close parentheses, then we have to decide what to do. So let's just start with what we know. We go from left to right. If it is a number, go straight to the output. If it is an operator, in this case, we just go straight to the operator stack. A number goes straight to the output. Operator times is greater than plus, so we just pile and push on top of plus. So far, nothing changed. Now, in the moment that we find an open parenthesis, this thing right here goes always to the top of the stack. We're going to open a new hierarchy level that needs to be performed before anything else. So as we open parentheses and we push this parenthesis right here in the operator stack, we continue the logic. So if it is a number, it goes straight to the output. Now, if it is a minus, we don't care about anything. We are inside a parenthesis, so we keep going and pushing this minus to the operator stack. A number goes straight to the output. And right here, as we find a matching close parenthesis, this thing right here, we're going to look, and everything that is between close parenthesis and open parenthesis, all the operators that are right here, in our case is just the minus, we're going to go and push all the operators to the output. So everything that was between open and close parentheses get pushed to the output. And we continue the same logic, right? Now we have this multiplication. Look, multiplication is level 2, which is less than or equals to whatever I had here on the top. So since it is less than or equals, I'm gonna send this top right here to the output, and only then the multiplication gets put on top of the addition. This new token multiplication that came from the input. All right, and we continue. 6 is a number, straight to the output. And now, plus. Plus has the level of precedence 1, which is less than multiplication and equals to plus. So both of these things, they will get sent to the output before we feed this plus into the operator stack. So we push the top multiplication to the output. We push now this top to the output. And only then my new token gets pushed to the operator stack. Beautiful. And finally, 8 gets pushed straight to the output. And we have to clean the operator stack and send the remaining last ones here to the output. And that should be the correct order of operands. Let's just quickly go ahead and let me just implement here that test, right? So everything that goes between parentheses has to be evaluated before. We have to just go and find everything between the start and the end, which means that for all the tokens in our split input, before I check for operators and precedence and anything, right here I'm going to say that if it is open parenthesis, so if my token is open parenthesis, this is easy, right? If it is open parenthesis, all I have to do is push to the operator stack, so upstack.append token. But else if the token is close parenthesis, now we have to go and loop back all the operators pushing to the output, correct? So if I found a matching close parenthesis, then I'm going to have to go and loop back until I found the matching open parenthesis. So while length of the upstack is greater than 0, right? So I have to go through all these things, but I look at that operator on the top, upstack.pop, and if this operator is an actual open parenthesis, so if I found the start of that end parenthesis, then I break the loop. Otherwise, I add all those operators inside the parenthesis to the output. All right, I think that's it. So if it is open parenthesis, all I have to do is add to the operator stack. If I find a close parenthesis, I have to go and loop back, popping all the operators, pop. If I found an open parenthesis, right? So if I found the matching open parenthesis, I break the loop. Otherwise, I keep appending to the output, sending those operators that I found between the open and close to the output. I think that's what it is. Let's see what else. I think that's it. Oops. Key error, open parenthesis. Right, so we could not find that operator in the precedence. Right, so there are two ways that we could fix this, I guess. We could add the open parenthesis as an operator with a precedence, let's say, super high. But we can also bypass if it is an actual open parenthesis in this case. It might be a little bit ugly, but I think it would do. So right here, while, yeah, so as soon as I find that operator on the top of the stack, I'm just going to test. If by any chance that operator is open, I'm going to break, correct? I just break that loop as well. That should do the job. All right, so if it was open and if it was closed right here, I think I'm only going to perform all of these things if it is not parentheses, right? So I'm going to come here and say else, and then all of these things get pushed to the right. So everything I do here, I only do if it is not open and closed parentheses, all right? Moment of the truth. Super cool. Right, so 3 plus 4 times 2 minus 1. If I open the Python REPL, how much is this? 35. I love it. So this is correct. The actual Python language result matches our expression result, so that is great news. 35, if we come here and we say something like, nothing stops us from saying 3.4, right? We can have a decimal number, right? 3.4 plus 4.88 divided by 2 minus 1 times 6, or even negative 6 plus 8. As long as we have spaces between these things, it should be fine. Let's just check. Minus 17.888000. Right. Ugly. But minus 17.8800. This is great news. You see, the fact that both Python and our Shunting Yard algorithm are giving the same result, that is absolutely great news. And we could call it a day and be happy and go home, but there's just one very, very small detail, very subtle, but it's there, right? Which is what happens with, let's say if we have an exponent operator, right? Something that kind of, we need to solve something like that, right? Something that has like, for example, 2 raised to the power 3 raised to the power 2. When you have this sequence of the same operator, right? So 2 raised to the 3 raised to the 2 and raised to something else. The question is, what is the result of this expression? There are 2 ways of looking at this, right? Are we going to perform 2 raised to the 3rd and then raised to the power 2? Or are we going to perform 3 raised to the power 2 and only then raise 2 to the result? Right? So it's almost like, are we going to go and put the precedence on the 2 raised to the 3rd and only then raise to the 2nd, so the result should be 64? Or are we actually going to go from the right, 3 raised to the power 2 first, and only then the result we go 2 raised to that thing, which is 512 in this case. What is the correct result? And the answer might surprise you, because look, if you studied mathematics, you will see that the result is actually this one right here. But we cannot really guarantee for sure, because you want to know what? Let me show you something. So let's just come here and say, let's just open the Python interpreter. If we open the REPL and I say 2 raised to the power 3 raised to the power 2, right? So this is the operator in Python to perform the exponent, right? So it is 2 raised to the exponent 3 raised to the exponent 2. This thing right here, it looks like Python computes things from right to left, right? So this is what we call right associativity, right? So this exponent operator associates from the right in Python. So it performs 2 raised to the 2, and then it raises 2 to the power 9, and then it gives us 512. And just to confirm, let's just open the Lua interpreter, the same thing. If I raise 2 to the 3 to the 2, right? So Lua uses the caret operator for exponents. And look at that. Great stuff. Right? So it looks like both Lua and Python agree that it is right associativity, but if we open Excel, and if I try to come here and say that the formula that I want is equals to 2 raised to the power 3 raised to the power 2. Look at that. So it looks like Excel decided to go from the left in this case. So again, it depends. There is no real absolute truth in this case. Everything depends on the parser that you use, right? The parser of your programming language, the parser of your whatever tool you're using. The parser is going to be the one deciding if you are going to associate from the left or from the right. In our case, I want to use this as an opportunity for us to talk to you about this kind of right associativity of the exponent operator, because everything else, right, 2 plus 3 plus 4, the plus operator associates from the left, the minus operator, 2 minus 4 minus 5 minus 7, also associates from the left. So everything associates from the left except this caret operator right here. All right? And you know what? I'm going to come here already to the source code and show to you what is the change that we have to do, because it is not that hard. The change is this. We're going to have, besides having the precedence operator, we're going to have something called, let's just say, let's call this thing right associativity. Let's just say that. Well, first of all, we're going to have a new operator, which is going to be the caret operator, that is going to have a higher precedence than everything else, right? This operator has to be evaluated before anything else, so precedence 4. And in the right associativity table, the exponent operator does associate from the right, and everything else does not. Does that make sense? So exponent associates from the right, it is right association true, and everything else is left, 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 and left. Because right here, as I am looping all the operators, in this test right here, I have two tests. The operator that I am looking at the token, right, at the input, is greater precedence than the operator that is on the top of the stack. So if this is true, I stop, but also I have to say or, and then I'm going to have a test here. Either that is true, or the right associativity of my token, right, the input that I'm reading. If it is right associativity, so if I'm talking about an operator that associates from the right, and the input token and the top of the stack has the same precedence, if the precedence of the input is equal to the precedence of the top of the up stack, if this was true, I already break. Otherwise, I have to go and test. If it is right associativity and the precedence is the same, then I also break and I associate from the right. Correct? So if I go up, and let's just say, changing side quotes, 2 raised to the 3 raised to the 2. As we saw, we expect this to associate from the right, and the result was, oops, I think I forgot to change our evaluation part, right, that postfix evaluation at the end. Did I forget something? Yeah, I did. So right here, I forgot. If the element is caret, then I have to go and Python is exponent operator right here. Cool. Was that it? Yes, it was. Beautiful. 512, it looks like our right associativity is now working correctly. I think that covers what I wanted to review from the whole Shunting Yard algorithm concepts, right? Look, Shunting Yard algorithm and solving expressions like this is usually just the first contact that we have, right? Whenever we are kind of really starting to learn about compilers, interpreters, formal languages. things get hairier really fast, right? If you're talking about compilers, you have to evolve not just simple expressions, but these expressions are going to be inside if statements, while loops, for loops, variable declaration, function call. So you have all these different things that you're going to have to start evolving from this, right? The Shunting Yard algorithm is just a very simple example of how we can start thinking about parsing an input, right? Tokenizing those things, having all this lexical analysis of what is a token, what is an operator, how do I identify what is a number, what is a variable. So it is kind of the first principles idea, right? We just have this starting conversation. As I always say, right, YouTube is not really a proper education platform, right? YouTube is probably, right now, is probably just trying to get your attention with all these thumbnails here at the right, trying to kind of distract you to go look at something else. So YouTube is not really an education platform. It kind of doesn't want you to stay here and really learn things deeply. As always, if you like this type of topic, remember that we do have proper structured long courses, right? We really dive into this topic of compilers. I just released a course on compilers. I think if you like this type of thing, if you like this kind of discussion, it's going to be super fun. I think you're going to enjoy this course. Other than that, I'm happy. I think we covered what I wanted to cover. All these little details, right, that we really take for granted and we don't think about it, right? Right associativity, left associativity, infixed, postfixed, Polish notation. So all these things, it was nice for us to talk, right? Just touch and go, right? Just a very quick conversation about these things. But I thought it was important. I think I wanted to leave these things written down. It's important for us to really understand what goes on in terms of like parsing these things, right? I don't know about you, right? I kind of look at this problem, right? The Shunting Yard algorithm, and I try to position myself and think, right, if I were back in 1961 trying to come up with these things, right? If Dijkstra didn't create this thing, would I be able to create something like that? Sometimes I would like to think so, right? Because look, it's all about deciding, right? If you have an expression, it's all about deciding. If I have this input with all these tokens, what gets sent to the output? How do I determine the order of those things? How do I send those things in the correct order to the output on the left? And also, by respecting the operator precedence, you have that other stack of operator stack that you can kind of just pile them there until they are ready to be sent to the output, right? I always like to think about the actual goal of what we're trying to implement, right? What is the actual goal of the Shunting Yard algorithm? And kind of going back, sitting down and trying to think exactly what is the prize that we're trying to accomplish is nice. I think it's very cool for us to go and reflect what the Shunting Yard algorithm is trying to accomplish. And hopefully you understood, or hopefully you liked the whole idea of how these things came to be, right? How everything kind of glues together for us to solve simple expressions. That was the whole goal. All right? Thank you very much for staying until the end. Hopefully, I will see you very soon in our next video. Thank you very much. See you soon.